What if I told you your entire existence is dependent on one small device you carry with you everywhere you go? You probably have the device envisioned in your head right now, but what you think is not entirely true. Your mobile phone is constructed of multiple parts all working in tandem with one another to allow you to do all your daily phoning needs. But one part is above all. It changed how we use electronics today and shaped the entirety of digital electronics. I'm talking about the transistor. But why? What makes that device so important? To put it simply, transistors have an ability to switch and amplify signals. It may not sound like a lot, but think about it. The ability to control the current running your device is a heck of a useful one in a world that runs on digital businesses. It lets us do all sorts of things, like building logic gates, the essence of all computers. But of course, transistors weren't always around, and it took quite a bit of experimentation to get where we are now. The first form of a transistor was called a thermoionic triode, or simply a vacuum tube, invented in 1907. It made all sorts of things possible, like radio technology and telecommunication. It differs much from a modern transistor, but the basic gist is there. There's a glass tube emptied from all the air to minimize the resistance. There's a rod placed in the middle of the tube and a plate circling around it. As voltage is applied to the rod heats up and starts emitting electrons within the vacuum tube, something known as an Edison effect. The electrons in the vacuum get picked up by the positively charged plate. The rod is called a cathode and the plate is called an anode. The process is one-sided, meaning the electrons can only go from the cathode to the anode. This is the early diode, an electrical component that can pass current in one direction. To make that diode into a triode, a concept of a transistor, a grid is placed in between the cathode and the anode. By connecting the grid to a power source, we can control its polarity, meaning it can either be negatively charged or positively charged. The electrons emitted by the cathode have a negative charge, so they interact with the grid. If the grid is negatively charged, a lot of the electrons will get repelled, and thus the amount that the anode picks up will decrease. A small amount of voltage on the grid is sufficient for a big current difference in the output. The vacuum tube is a very fragile and power-consuming device, however, a far cry from our modern transistors. Its use of thermionic effects is not the most efficient way to control the current. That's why an Austro-Hungarian physicist, Julius Edgar Lilienfeld, patented a field effect transistor, which uses electronic processes instead of thermomechanical ones, as a suitable replacement first in Canada in 1925, then the US in 1926 and 1928, but his lack of working prototypes or research papers meant that the field effect transistors wouldn't see the light of day for another 2 decades. In 1947, two Bell Labs scientists from New Jersey, John Bardeen and Walter Bartain, led by William Shockley, created the first point-contact transistor, which produced greater output than the input. It used 2 gold contacts and a crystal of germanium. It wouldn't be until 9 years later when they received their joint Nobel Prize for their research on semiconductors. They still didn't manage to create a field effect transistor, however, as they couldn't get over the surface states, which basically block the electric fields that are essential for a field effect transistor. A different group of German physicists, Herbert Matare and Hrcky separately invented the point-contact transistor, but upon learning that they were already beaten to it by Shockley's team, their company rushed to get its transition into production for amplified use in France's telephone network. In 1950, another type of transistor would be invented by chemists Gordon Thiel and Morgan Sparks. It was a bipolar junction NPN transistor, which used a process known as doping. Basically, there are 3 kinds of materials in terms of electric conductivity. There are conductors that conduct current when a power source is connected to them, there are insulators, they block current, and there are semiconductors. They are in between the two, not being fully conductive nor fully insulative. So to make them closer to conductors, we dope them with certain materials that improve their conductance. There are 2 types of semiconductors, p-types and n-types. The way we dope semiconductors is by fusing them with other materials. If we want a p-type, we will fuse 4-valent semiconductor materials with 3-valent ones, meaning there will be a deficit of electrons. On the other hand, if we want to get an n-type, we fuse 4-valent materials with 5-valent ones, meaning there will be a surplus of electrons. Note that both the n-type and the p-type are neutrally charged, meaning they have equal amounts of protons and electrons, but the p-types have 1 extra space they can hold an electron, while the n-types are oversaturated and they cannot hold any more electrons. A valency is basically how many electrons does an atom have to react with other atoms. If it's getting confusing, that's because it is. These 2 types can be combined into a p-n junction. How? It doesn't matter, who cares? Between the 2 types of semiconductors, there is something known as a depletion region. It acts as a barrier of high resistance that blocks current. To get over that barrier, a voltage must be applied to it with the p-type connected to the plus and the n-type connected to the minus terminal of the battery. That will completely remove the barrier and let current flow. That's called forward biasing. Reversing the polarity will make the barrier even stronger, and that's called reverse biasing. Remember the diode I mentioned at the start when I was explaining the vacuum tube? Yeah, that's it. It works the same way. Connect it one way and you have current flow. Reverse it and the current stops. So if we slap another n-type, we get an NPN junction, or more familiarly called transistor. The first N is the emitter, the P in the middle is called the base, and the second N is the collector. To activate the transistor, we forward bias one side of the transistor and reverse bias the other, which gives us current flow which is controlled by the small base current. Just how the vacuum tube's output current is controlled by a small voltage on the grid. If all of that is confusing, that's because I'm speedrunning an entire semester of high school electronics. The vacuum tube is much simpler in practice, that's why it's not used anymore. Besides, this is more of a history on transistors rather than a science made simple video. And this is where I end the first part of this two-part series on transistors. It initially should have been one video, but it took me a week longer to make this video, and I'm still on like 50% done. So yeah, I'm releasing it now as part 1, and part 2 is coming maybe in a week or two. Next part is about field effect transistors, and yeah, I hope you enjoyed the video, and please like, share, subscribe, and all that shit. And yeah, see you in the next one.